Swayam Prabha. Digital India. Educated India.
Welcome back to another lecture of this course on robust control. So from today onwards we are going to start looking at some preliminaries, some basic material that we are going to brush up on, which you are already probably familiar with when you attended first course on control systems. However, we hope that we shall see it in a new light. We shall begin to take a fresh perspective on these things that you are already possibly aware of, and hopefully that will give you some new insights into these notions. Chief among these notions being the idea of controllability. Okay, so we are going to start looking at a state space model of a physical system, a linear time invariant system. Okay, we will get into the definitions of time invariance, causality, etc. in a little more technical manner in a few lectures from now, but for now we understand them in the way that any person who has undergone an undergraduate course on control systems is supposed to understand, right. So we know that the state space description of a system, of a linear time invariant system, is given by this. So where we will differ slightly from this undergraduate notion is, in the undergraduate controls course we mostly talk about seesaw systems, right. So in that case this u would be a scalar, yeah, a single input. The y would also be a scalar, a single input. Now unlike in the undergraduate level, here we are going to generalize this notion to include m inputs and p outputs. So in other words, what that implies is essentially, of course, as usual, xt is an n tuple, y is a p tuple, u is an m tuple, okay. And accordingly, of course, then we have A being an n cross n matrix, and B has to be, well, of course, n cross m matrix. C has to be P cross n matrix, right, and D has to be a P cross m matrix, right. You can check that upon multiplying the sizes of the corresponding entries, they are conformal here, right. Okay, so that is the most generic state space description that we have for any linear time invariant system. Now given this, we also know that whether it is MIMO or seesaw, right, that the solution of this, at least the x part, is given by e to the a t minus t naught times x t naught plus integration from t naught to t e to the a t minus tau b u tau d tau, right. So there are two parts to this response, or this solution as we call it, of course, of which the first part, yeah, the first part that I am now marking out in yellow is what we call the zero input response, all right. And the second part, let me use a different color, is what we call the zero state response of the system, right. So, in other words, if your initial conditions were 0, then only the second part which I marked in red would be the entire solution of this state, yeah. And on the other hand, if your input, your applied input was 0, there was no externally applied input like u, then the yellow part that I have marked, the 0 input response, would have been all that would be there to this response, right. So, this first part is what we call the response of an autonomous system. So, there is no external input that is being applied here, you just have some potentially non-zero initial conditions in your states, and you want to study how those states evolve thereafter, right, from the instant of time demarcated by t naught onwards. So, that is called the response of the autonomous system, okay. So, you exclude the effect of the input on the overall response, all right. So, that is how we sort of split up the solution of this state space equation into two distinct parts. Of course, if you are particular about the what you call a solution to this, then you would say, well, hang on, the solution is after all not x but y. So, all you need to do is to pre-multiply this x by C matrix, the C matrix that we have defined here, that is this one, yeah. So, you pre-multiply this x by the C matrix and you have your y. So, essentially if you solve for x, you have also got your y effectively, right. Okay. So, that being said, we have not defined one important quantity, which of course again I assume you are familiar with, that is this matrix exponential. So, this is not like the scalar exponential which you already are aware of, which is a function. This matrix exponential has to be defined, okay. We define it, it is not something that follows naturally. How do we define it? So, the matrix exponential is defined as I plus at plus at whole squared by factorial 2 plus the generic term is at to the power k upon factorial k, and this goes on till infinity ad infinitum, right. So, this is how we define this, yeah, and it turns out that this indeed, you can check now, you can plug this back in and you will see that it indeed satisfies the solution, the state equation, that is. So, this solution indeed satisfies the state equation that I have given here, right. So, this behaves in a manner very similar to the scalar exponential function when we solve for first order differential equation, right. But it is not exactly something that follows naturally, it is something that we are defining, okay, because remember each of these fellows is a matrix, right. So, this is an important property, and this is also called the state transition matrix, okay. It has some very interesting properties which we are now going to focus our attention on. So, notice that if you take d dt of e to the at, in the sense that when you say you are taking the derivative of a matrix, you are essentially taking entry wise derivative of that entries of the matrix, right. So, this is a derivative of a matrix with respect to a scalar. So, each entry of the matrix is a function of that scalar. If you are taking a derivative of that matrix, it just means that you are taking individual derivatives of the entries, yeah. So, you can clearly see then this at means that each entry of the A matrix multiplied by t, at whole squared means each entry of A squared multiplied by t squared, right. But A squared and A and all of these are after all constant matrices, right. So, therefore, it stands to reason, or it readily follows from this definition, yeah. So, remember I have just marked it out. So, this is a definition. So, it follows from this definition that if you differentiate this, what you will end up getting is A plus 2 a squared t by factorial 2 plus dot dot dot. You can take the kth term, you will see k t to the power k minus 1 a to the k by factorial k plus dot dot dot. So, you take this typical term and you see what it looks like. Yeah. If you focus your attention just on this term, what can I write this term as? I can write this term as t to the power k minus 1. Let me pull out the k outside, a outside, one of these a's outside, because after all this is just a scalar, right. So, I can obviously commute the multiplication of a scalar with a matrix. So, a scalar times a matrix is equal to the matrix times the scalar. So, yeah, so I can just play around with this, and this k I am going to cancel out with this factorial k, so that I am left with only factorial k minus 1 below and a to the k minus 1, right. So, now having seen that this can be written in this fashion, we now resume and we can say that we can take this a common out, and then this is nothing but a summation of t to the k minus 1 by factorial k minus 1 a to the k minus 1, where k runs from basically 1, k runs from 1 through infinity, right. Because remember, what is this term? Yeah, if you look at the first term here, it is t to the power 0. So, that means k minus 1 is 0, which means k is equal to 1. But this we can easily then write as, by shifting this index, I can just write this as k is equal to 0 to infinity t to the power k upon factorial k times a to the power k, right. But this is nothing but what we have defined to be our e to the at. So, this turns out to be a times e to the at, right, and that is a very important and significant property of this so called state transition matrix, which is what essentially leads to the fact that this is a solution of the state equation that we have claimed earlier. Okay. So, you have to use this property. So, this is an important property of the state transition matrix, okay, the matrix exponential. Okay. Let us look at another interesting property, e to the at whole conjugate. Yeah, this is nothing but I plus at plus a squared t squared by factorial 2 plus dot dot dot, the whole conjugate, right. So, this just means I plus a conjugate t plus a squared conjugate t squared by factorial 2 plus so on. But what does this essentially mean? You can play around with the order of these two operations. Yeah, you can take a squared first and then take its Hermitian, or you can take a Hermitian first and then take its squared, it does not really matter. So, in other words, this basically means this is I plus a Hermitian t plus a Hermitian squared t squared by factorial 2 plus dot 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 so on, and this essentially means it is e to the a Hermitian t, right. So, what I am essentially saying is that if you want to find out the Hermitian of the matrix exponential, you just take the Hermitian of the individual matrix and then raise it to its exponential as per the definition that we have given, like so, right. So, this is a second sort of important property of this transition matrix, right. Now, the third and final property, this is going to be really handy, but also we should be a little cautious. So, if A1 and A2 commute, that is A1 A2 is equal to A2 A1, these two matrices, right, then e to the A1 plus A2 t is equal to e to the A1 t times e to the A2 t. Okay. So, I am just writing the if part here. It turns out it is an if and only if condition, right. So, unlike in the scalar case, remember, so this is where you have to be very careful. In the scalar case, you remember you have e to the x plus y, you can always write this as e to the x times e to the y. but matrix multiplication is a little special, right. So, in the matrix case, you do not generally have e to the m plus n is not in general equal to e to the m times e to the n unless mn is equal to nm. Yeah. So, that is a very important thing to remember. So, in general you cannot just have the matrix exponential of a sum of matrices and which can be split up into this matrix exponential of the individual matrices multiplied with each other. Yeah, that is not in general true. Only true if the matrix multiplication between those two matrices whose exponentials you are interested in, those matrices individually commute. Okay, right. So, these are some of the important properties. Okay. So, now that we have come this far, let us try and recall from some of the initial results we had about matrices that are diagonalizable. So, suppose a matrix is diagonal. So, that is lambda is equal to, let us say, lambda 1, lambda 2 dot 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 till lambda n. Then what can I say about e to the lambda t? Yeah, it is going to be I plus lambda t plus lambda squared t squared plus dot 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 upon factorial 2, of course. So, you look at each individual entry then, yeah, and this is very easy to figure out. You will see that each individual diagonal entry just turns out to be nothing but lambda 1 t plus lambda 1 squared t squared by factorial 2 plus dot dot dot. Likewise, the last term would be 1 plus lambda n t plus lambda n squared t squared by factorial t 2 plus dot dot dot, right. So, each of these individual terms then converge to e to the lambda 1 t dot 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 till e to the lambda n t. So, in other words, if a matrix is diagonal, then finding out its matrix exponential is simple, right. What if a matrix is not diagonal but diagonalizable? Okay. So, that is the second level of complexity, but really not very difficult to see. So, let us say, suppose A is not diagonal but diagonalizable. Yeah. Then there exists T such that T inverse A T is equal to lambda, where lambda is a diagonal matrix. Then what do we do? Well, we notice that A is equal to T lambda T inverse. So, A squared is equal to T lambda T inverse times T lambda T inverse, so on till we take the generic term A to the k is equal to T lambda T inverse, T lambda T inverse dot dot dot, likewise T lambda T inverse. Yeah. So, k times like this. But notice that if you pull together terms like these together, then they pulverize each other, right. So, what will then be left with eventually is nothing but T lambda to the power k times T inverse. So, therefore, e to the A t is equal to I plus A t plus dot 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 plus A to the power k t to the power k by factorial k plus dot dot dot. This turns out to be this T I can write as T inverse, yeah, that is identity, plus T lambda T inverse T plus dot 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 T lambda T inverse, sorry, lambda to the power k T inverse times T to the k over factorial k, that is the generic term. So, let me pull out the T from the left common and the T inverse from the right common. So, I have the t pulled out from the left, I am left with identity plus lambda squared t squared by factorial 2 plus dot 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 till lambda to the k t to the k by factorial k plus the infinite expansion and the t inverse pulled out from the right common. But what is there in between, sandwiched between this t and t inverse, is already known to me. It is very easy to deal with. I have just shown you that if a matrix is already diagonal, then it is very easy to get its matrix exponential. So, what I will then be left with is a matrix that looks something like e to the lambda 1 t, e to the lambda 2 t dot 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 till e to the lambda n t, where of course these lambda 1 and lambda 2, lambda 3, these need not be distinct. If they are distinct, then of course it is always diagonalizable. Even if they are not distinct, yeah, we can still have a diagonalization, that is still possible. We have seen that earlier when we discussed matrices, this Jordan forms, right. So, the next case, so we have seen if a matrix is already diagonal, it is a straightforward case. Even if it is not diagonal, but it is at least diagonalizable, even then there is an easy way to handle this matrix exponential and evaluate it. Now, suppose that the matrix is neither diagonal nor is it diagonalizable. Suppose A is not diagonalizable, yeah, then what is the best we can do? The best we can do is to get it down to its Jordan form, yeah. So, what is this Jordan form? Well, the Jordan form would be something like J1, J2 dot 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 till JL maybe, yeah. And what do those individual Jordan blocks look like? So, you take any Ji, it looks something like lambda I sitting on the diagonals, and the super diagonal has 1 1 1 like this, everything else is 0. So, this now I can write down as lambda I times I plus 0 0 0 on the diagonal, everything else 0 here, only the super diagonal has ones and like this. So, let me call this sort of a matrix as N, yeah, Ni maybe, okay. Suppose this is of size, what should I call it, maybe Ni cross Ni, yeah. So, J1 is of size N1, J2 is of size N2 across N2, JL is of size NL cross NL, where, okay. So, this is how we describe it, right. So, we are going to first look at these individual blocks and see if there is an easy way of getting their matrix exponentials, and once we have done that, finally we will see that after all getting the matrix exponential for the A matrix is also not a big deal, okay. So, we will break it down into smaller steps. So, first step, what about these individual Jordan blocks? Is there an easy way to get the handle over this? Notice first that lambda I times I and Ni commute, yeah. So, that means that is lambda I times Ni is equal to Ni times lambda I times I. The reason is obvious, lambda is just a scalar. So, multiplication of a matrix with a scalar is commutative, and the identity is after all just the identity, whether you post multiply by an identity or pre multiply by an identity to a square matrix, it just returns the same result, right. So, this is evident, straightforward to check. But what does that imply? If I were interested in finding out e to the JIT, yeah, then I would be essentially looking at e to the lambda I plus n times t. Now, in general, remember a while back I told you this property of this matrix exponential, that in general if you have e to the m plus n, yeah, unless they commute you cannot write them in this fashion. It turns out in this case they do commute, and because they do commute we can write this as e to the lambda I times t multiplied by e to the nt. Now you might wonder, how is this going to help me? Yeah. Well, for one, this is after all a diagonal matrix, this lambda it. So therefore this matrix exponential is very simple to get. You just write it as e to the lambda it, e to the lambda it dot 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 till e to the lambda it. Yeah. And then you have this e to the nt to deal with, and apparently at this juncture we are still stuck, because what is after all special about this n? Well, here is what is special about this matrix n. Look at this matrix n. Let us take the 3 by 3 case, and the general case will be very straightforward, simple. 1 1 0 0 0 0 0. Okay. Look at n squared. What is n squared? You can just check. I already know it, so I am not going to compute it through hand computation, but you can check that this is going to be 0 0 1 0 0 0 0 0 0. And now if you go to n cubed, this is going to be the matrix of all zeros. So this is a matrix that we call as, this matrix is what we call as a nilpotent matrix, which means that you raise it to a certain power, yeah, then for that power it leads to the zero matrix. Yeah, it just reduces to the zero matrix, and beyond that, of course, you raise to any higher power, it keeps getting to a zero matrix. So then, what is the pattern you observe here? If this is of size 3 cross 3, the maximum power to which this can be raised until it becomes a zero matrix is 2. So what is the size of this n matrix? This matrix ni, sorry, I should say ni, ni. Yeah, what is the size of this matrix ni? Well, it is the same as this size of this J block, right? So this is of size small ni. So then I know that n raised to the power ni is going to be the zero matrix. Yeah, and beyond that there is no point in carrying on. So now this gives us a very nice handle, because then we know that unlike the conventional matrix exponential which carries on till infinity, this fellow need not have an infinite expansion. It will not have an infinite expansion. It will only expand till as far as the power goes up to small ni minus 1 and t raised to the power small ni minus 1 upon factorial ni minus 1. That is it. So this is just a finite sum then, right, and this is what makes this so easy to deal with, because now we know that plugging in this result, e to the jit will just become something that we can write down in this straightforward fashion, lambda it e to the lambda it dot 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 e to the lambda it times this sum, which is nothing but I plus nit plus dot 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 till the last term would be ni to the power ni minus 1 t to the power ni minus 1 upon factorial ni minus 1. Yeah, that is all there is to it. So now whether a matrix is diagonalizable or not, we have seen at least the general form. Oh, hang on, we have not seen that yet. So this is just e to the jit. So now you might wonder that if a general matrix A can be gotten into this Jordan block form, and each individual Jordan block we know what it looks like, then does it really help us? Well, you bet it does. How? So we can then write this A as each of these Jordan blocks, let me write them as lambda 1 I plus n1. The second block and so on till the last one will be lambda li plus nl, right. Okay, the rest of the blocks will all be zeros, alright. So what about a squared? If I try to do a squared here, take this as an exercise and check that if you do a squared here like this, multiplication by block matrices, especially diagonal block matrices, yeah, it will lead to the similar kind of result that you get for individual diagonal matrices. In other words, if you now write, okay, let me do this one step and then you can carry on with the next step. So lambda 1 I plus n1 dot dot till lambda L I plus nl times lambda 1 I plus n1 dot 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 till lambda L I plus nl. Okay. All right. Now, if you want to multiply this, what do we get? You multiply this with this, then all the rest are zeros. So, you basically just see that this ends up with lambda 1 I plus n1 whole squared, right. So, now notice that what does this lead to? Okay, let us just for the sake of completeness, let us check the second one. When you take the second block, yeah, you will see it is going to lead up to 0. So, what I am saying is that essentially this leads us to same type of results like we would have obtained for diagonal matrices rather than block diagonal matrices. Only thing is that here what is sitting at the diagonal is not a single scalar, but rather a matrix itself. Yeah. So, this then it turns out that if you try to do this summation a to the power k t to the power k upon factorial k for k going from 0 through till infinity, which is how we define e to the at, yeah, then what we will end up with is basically some accumulation or aggregation at the block diagonals, right. Of course, I have kind of forgotten about this. So remember, I have already taken this to be in the Jordan form. The original matrix may not be in the Jordan form. The original matrix is in some form from which you take a similarity transformation to get to the Jordan form, like we did a similarity transformation to get to the diagonal form. So here I am already starting with the Jordan form. If you are not given the Jordan form, then you first transform it to the Jordan form, and then you will accordingly have this T A T inverse or T inverse A T, whichever. T inverse A T is going to be equal to this Jordan form. And then if you want to get the matrix exponential of A, you have to pre-multiply and post-multiply by suitably T or T inverse. Yeah. So that part I am ignoring. Yeah, that part you can obviously handle. But the basic idea is that if you are trying to get this exponential for a matrix which is already in the Jordan form, then you see all that's happening is all the story is unfolding at the block diagonals only. And what is unfolding at the block diagonals? This is nothing but, you see, J1 squared. This is similarly JL squared. So then it did make sense what I did just now, right? Which is I just looked at the individual J blocks. Yeah, and I told you that once I have this picture complete as to how to handle this beast, then I can handle this bigger beast, because it is nothing but a replication of that smaller Jordan block. Whatever is happening to the smaller Jordan block, I just replicate it at each block diagonal and I have the complete picture, right. So therefore, this e to the at will look nothing but like this, where you have this e to the lambda 1 t dot 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 e to the lambda 1 t, and then this finite sum, right, I plus n1 t plus dot 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 till n1 to the power small n1 minus 1 t to the power small n1 minus 1 upon factorial n1 minus 1. Yeah. So each of these individual, whatever you did to the individual Jordan blocks, now you do to the individual blocks here in this big matrix and place them there. That's it, right. So we've given you a general method. Remember, if you've done a course on basic control systems at the UG level, you probably learned how to get this matrix exponential using Laplace transforms, right. But here we are not going to use that. We are just going to give you a complete linear algebraic approach to this through the state space method itself, and now you know how to get the matrix exponential for any matrix without having to resort to Laplace transform at any stage, right. Okay. Before we conclude this discussion about how to get the matrix exponential, there is another result that I want to discuss, and that will also give us a method for evaluating this matrix exponential, which is by means of the Cayley-Hamilton theorem. Okay. So, I am not going to obviously prove the Cayley-Hamilton theorem, you can look it up in any standard maths textbook that you might have encountered. So, what the Cayley-Hamilton theorem says is that every matrix, by the way, let me warn you that the proof is not as straightforward as just plugging in A in the characteristic equation in the expression using the determinant. Hang on, let me, maybe I am getting ahead of myself. So, every matrix satisfies its just a minute, its characteristic equation. Okay, so suppose you have a matrix A, then the characteristic equation of the matrix A is given by determinant of Si minus A. Yeah. So, this is the characteristic polynomial. Yeah, this is the characteristic polynomial, and the characteristic equation is given by chi-as is equal to 0 by equating the characteristic polynomial to 0. So, you might be tempted to think, hang on, this is very easy, I am just going to substitute A instead of S, and A times I is just A. So, A minus A, and that is determinant A minus A, and that is 0. No, that is not a proof, that is a pretty illegitimate sort of an operation that you are doing here, because remember S is, I mean, you cannot really just substitute a matrix in place of a scalar and do this sort of an operation, that is not allowed, right. So, the proof of this Cayley-Hamilton theorem is not as trivial as it might appear at first glance, and we are not going to indulge in proving this. Okay. There are several excellent textbooks that have dealt with this already. So, at this point we just expect that you look this up from some standard book to convince yourself that this is a legitimate result, that every matrix satisfies its characteristic equation. What is the consequence of this? What do we know about a characteristic polynomial? The characteristic polynomial of a matrix, remember, the characteristic polynomial of a matrix is a monic polynomial. Monic polynomial, what do I mean by that? The coefficient of the highest degree is unity of degree n, where A is of size n cross n. Yeah. So, obviously a monic polynomial of degree n, if a polynomial has degree n, it has n roots. Yeah, and those n roots are exactly the eigenvalues as we have discussed earlier, right. This is just a reprise of what we have already gone through while discussing matrices. Now, the point is that if, because of this Cayley-Hamilton theorem, what we can say is that A to the n plus some alpha 1 A to the n minus 1 plus dot 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 till alpha n I is equal to 0, where determinant of Si minus A is equal to s to the power n plus alpha 1 s to the n minus 1 plus dot 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 till plus alpha n is equal, So, if this is the characteristic polynomial, then you have the fact that the characteristic equation is satisfied by the matrix itself. Okay. What is the consequence of this? The consequence of this is that for any power of A, when A is raised to any power greater than or equal to n, I can always write this as a linear combination, with a minus sign, let me put it. I can always write this as a linear combination of I through A to the n minus 1. Okay. So, here is how: minus alpha 1 A to the n minus 1. Okay. What about for A to the k, where k is greater than n? I can write that as A to the k minus n times A to the n, which is nothing but minus alpha n a to the k minus n. Remember, k minus n is now a positive integer, minus alpha n minus 1 a to the k minus n plus 1 minus dot 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 minus alpha 1 a to the power k minus n plus 1, right. Excuse me. Right. So, I can always write this in this fashion. So, in other words, I can write a to the k as a linear combination of fellows from linear combination of a to the k minus n, a to the k minus n plus 1 dot 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 till a to the k plus 1. I hope that is what it is, and I have not goofed off here in this calculation, right. Yeah. So I think it should be minus 1. I just made that mistake here. So, it should be k minus n plus n minus 1, right, plus n minus 1. Yeah, that is what it is, k minus n plus n minus 1. Yeah. So, that will basically be this n and n cancel out. So, it is going to be k minus 1. Yeah. So, it is k minus 1, right. But then notice that if I now look at k minus 1, yeah, this is like a reverse kind of a proceeding to what you generally do in mathematical induction. So, now a to the k minus 1 can also be written as, so long as k minus 1 is greater than n, the same step can be carried out. So, k minus 1, now similarly, let me write that down. Similarly, a to the k minus 1 is equal to linear combination of a to the k minus n minus 1, a to the a to the k minus n dot 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 till a to the k minus 2, right. Yeah, right. So, that is the way to write this. So, as long as provided, of course, k minus 1 is also greater than n. So, eventually at some point I will reach k minus some number is equal to n, and the moment I reach that, I know what the expression is, I can have this expression. So, I can plug it in. So, remember, each time I am plugging this expression in, I am writing it as a linear combination of the powers of a from 0 through till n minus 1. So, that way I get to the power of a to the n. Now, any power of a greater than n can be written in terms of only I through a to the power n minus 1. That is the big conclusion. And how does that help us in so far as what we are doing here? Remember that we are saying that e to the at is an infinite sum, right, is an infinite sum we have defined as summation a to the k t to the k by factorial k going from 0 to infinity. But now we are saying that look, you do not really need to go through till infinite powers, because for every power of a, that is for k ranging from the number n through till infinity, every single such power of a can be reduced or represented in terms of the first n minus 1 powers of a and identity, right. So, of course, then we do not know what the coefficients are. If it is a linear combination, then there is the basis and there is the coefficients, or rather there is the vectors and there is the scaling factors of the vector. So, what are the scaling factors? The point is, in theory, we should then be able to write this as some summation of some phi t, or rather phi I t, a to the power, or rather phi k t maybe, a to the power k, where k ranges from 0 all the way up to just n minus 1. So, we should be able to write this as a finite sum, right. So long as we absorb this time dependence in this function phi, Yeah, I do not need to look for any more functions than these n functions which serve as coefficients of I, a squared, a cubed till a to the power n minus 1. Yeah. So, I should be able to write this in this finite way. This is the what we are positing, right. Now, then the problem of evaluating this matrix exponential boils down to our ability to evaluate these coefficients. Please remember, we have already shown you one method, which is through diagonalization or Jordan block form representation. We have already seen how to get the matrix exponential. Now, this is the second method that we are trying to present, whereby we are saying that by dint of the Cayley-Hamilton theorem, every such function can be written in this manner. Yeah, we do not need to look for any powers of a beyond n minus 1. Okay. Now, if that is true, then I am now going to say another, I am going to now claim another result here. Okay. It might seem like a digression for the moment. Let us draw a line below this, we will revisit this very shortly, but before that let me just draw your attention to another result. So, suppose Fs and Gs are two functions in C such that Fs is equal to Gs whenever S is an eigenvalue of A, a matrix. Okay. Then f of A is going to be equal to G of A. So, a very succinct way of putting this is, if two functions agree on a spectrum of a matrix, yeah, then they equal when you substitute the matrix itself as the argument. When you pass on the matrix as the argument of those functions, they must equal. Why should this be so? See, what is this saying? Again, we are not going to state this like a formal theorem proof kind of environment, but what essentially this is saying is, if f lambda I is equal to G lambda I. So, okay, let me just give this the veneer or appearance of a proof. So, if f lambda I is equal to G lambda I for lambda I, or rather whenever lambda I, where lambda I is an eigenvalue of A. Okay. So, then what can we say about Fs minus Gs? What can we say about Fs minus Gs? This is very interesting. So, Fs minus Gs is some function, say psi of S, which vanishes exactly wherever you have eigenvalues of A. So, that means psi of lambda I is equal to 0. Yeah, because that is exactly what it means to say that f of lambda I is equal to G of lambda I. Therefore, psi of S must have a 0 at lambda I. It is just the same way as saying this. Therefore, psi of S must be some again, what function should I choose? H equal to some H of S times the characteristic polynomial. I do not know what H of S is, it could be a constant for all I care, it could be anything. But the point is that this psi of S can vanish at other places also, but at least wherever S is equal to an eigenvalue of A, it must vanish. So, therefore, it must have exactly the roots, the same roots as the characteristic polynomial of A, right. It could have other roots as well characterized by H, but at least whatever is a root of the characteristic polynomial must also be a root of this psi. So, therefore, it implies that Fs minus Gs, or rather in one step I can write Fs is equal to Gs plus Hs times this chi s. right. Now how does this help? You might wonder, how does this help? So now if I substitute, okay, let me get rid of this, let S be replaced by the matrix A, then what do we get? Then we have that f of A is equal to G of A plus H of A times chi of A. But by Cayley-Hamilton theorem we already know that this fellow must vanish. So therefore you have that f of A is equal to G of A. So in other words, we have eventually ended up proving this claim that we just made a while back, to the effect that if a function agrees with another function in the spectrum of a matrix, then those two functions must equal each other when you pass on the matrix itself as the argument. Okay, right.
So strictly speaking, however, we need not use the characteristic polynomial for this purpose, for the purpose of this proof, right? But because we haven't dealt with something called as a minimal polynomial, so in case your matrix ends up having repeated eigenvalues, then it is actually the minimal polynomial, which is the lowest degree polynomial, that vanishes when you pass on the argument A instead of S, that is the matrix A instead of S, right. But since we haven't dealt with that minimal polynomial, I have actually used this characteristic polynomial in this proof. But if you are familiar with something called as a minimal polynomial, then that mu of S should be used here in your proof, and it would still go forth exactly in the same manner. Everywhere wherever I have used this characteristic polynomial, just go ahead and replace it with a minimal polynomial. It is actually the so called the generating element of the annihilating ideal, okay, of a particular matrix or operator, okay. But you need not bother with those terms since we haven't gone that far into describing what minimal polynomials and their properties are. So for the time being, we will just deal with a simple case where we will assume that the minimal polynomial is the same as the characteristic polynomial, which is true of essentially diagonalizable operators, okay. But this proof works even if your operator or matrix is not diagonalizable.
Now in so far as evaluating this matrix exponential goes, how are we going to help matters? So you see, recall just a while back, what did we write here? This is one of our functions and this is another of our functions, alright. Okay, so how are we going to use this result that we have just seen here? Yeah. So we remember we are trying to evaluate these phi k's, right? These are the unknown coefficients, all right. So how do we know in the first place that these fellows are equal? Well, that's a given. Again from Cayley-Hamilton theorem, remember the thread of reasoning. Again from Cayley-Hamilton theorem, we know that these two fellows are equal. If these two fellows are equal, shouldn't the reverse also be true? Yeah. If these fellows are equal, yeah, so if two fellows agree when you pass on the matrix as an argument, shouldn't it also be true, just think about it, shouldn't it also be true that they must agree on the spectrum of the matrix? Yeah. It's quite straightforward. It's actually easier to prove than this more complicated result or this trickier result that we have proved here, right? So what we have proved, we are going to use the reverse of that result, which is actually easier, but this goes both ways. So we are saying that if two functions equal when you pass on the matrix as an argument, then they must agree on each and every eigenvalue of the particular matrix as well. Yeah. So why can we claim this to be true? Well, for one, you have to just notice that every function can be expanded. Yeah, every analytic function. So this is the one bit of small result that we use. Every analytic function can be expanded in a series, right? So we take any two of these functions, complex functions, suppose they agree on this matrix A, right? And then you expand both of them in a series, yeah, around some, so you expand both of them in a series. Once you expand both of them in a series, then they are both basically infinite series on either side, right? And now you are saying that if they agree on this matrix A, then you pass on this matrix A in this series on either side. Yeah, and again you see that they become finite series to an extent, right? Because you don't need to look for any powers of A higher than n, or rather n minus 1 in fact, right? So then if they agree on this matrix A, shouldn't they also agree on the eigenvalues of A? Because remember, every time you raise A to some power, you also end up raising, so it is because of this result that A can be transformed to a diagonal matrix or to a Jordan matrix, right? So every time you take this S and substitute it with A, you could as well substitute it with T J T inverse. So that is what A is equal, right? So suppose you have two functions which agree on A, yeah, then you pass on this. So suppose f of A is equal to g of A. Now it is the reverse. So that means that f of T j T inverse is equal to g of T j T inverse. Yeah, and now if you expand both of these f and g as polynomials, as a series, yeah, right, not polynomials, as a series on either side, then you see that if on either side they have to be equal, then they must agree on each of the eigenvalues, because otherwise you are never going to have the condition that f of T j T inverse minus g of T j T inverse is equal to 0, yeah, which just basically means that if you are considering their series expansions, then you can take the T out common from the left like we did for polynomials and the T inverse out common from the right, and in between what you will be left with is just this j minus the f of j minus g of j, right. So f of j minus g of j cannot agree unless f of lambda 1 is equal to g of lambda 1, f of lambda 2 is equal to g of lambda 2. So the only tool that you need here is the fact that any function which is analytic can be expanded in a series, yeah, that is the property of a complex function. So that is the only property, right. So we have assured ourselves that if a function agrees on a matrix, then it must agree on its spectrum, and if a function agrees on its spectrum, it must agree on its matrix, okay. So our target now would be to cook up functions that agree on a spectrum of a given matrix, and then we can say that those two functions will also agree in the matrix itself, right. So on one side we choose f is equal to e to the st, and on the other side we choose g to be equal to, on the one side we choose this, and on the other side we choose this to be equal to phi naught t plus phi 1 t times s plus dot 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 till phi n minus 1 t times s to the n minus 1, okay. And we claim that if we can show that these two functions, if we make them agree on the spectrum of A, right. So each time we substitute s as lambda 1, lambda 2, lambda 3 dot 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 till lambda n, we get a set of equations for these, right, and each time we get that equation, if we can show that they are true for all of those cases of lambda 1, lambda 2, lambda 3 till lambda n, then we must have that f of A. So if f of s and g of s equal each other for s in the set lambda 1, lambda 2 dot 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 till lambda n, these are of course the eigenvalues of A, then f of A is equal to g of A, and we would have actually got an expression, a finite series, yeah, a finite sum rather, which actually equals the matrix exponential. So this is an alternative way of getting the matrix exponential to what we have already learnt earlier, right. So what I am saying is that look, this e to the lambda 1 t is going to be equal to phi naught t plus phi 1 t lambda 1 plus dot 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 till phi n minus 1 t lambda 1 to the power n minus 1. So, this is for first equation. Second equation would be e to the lambda 2 t is equal to phi naught t plus phi 1 t lambda 2 plus dot 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 till phi n minus 1 t lambda 2 to the power n minus 1. So, likewise you can keep going till you get the, so remember these eigenvalues need not be distinct. So, then you might wonder there is a problem, and we will just finish off by convincing you that even then you can still end up getting n equations in n unknowns. Lambda n to the power n minus 1. Yeah. So, then we can write this in this fashion, where we have that phi naught. So, I am dropping the argument in t, you okay, let me not drop it, that might create some confusion. So, let me have all the arguments in t like so, and what we will then have is 1 lambda 1 squared dot 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 till lambda n squared lambda 1 to the power n minus 1. Yeah. Till the second row is 1 lambda 2 squared dot 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 till lambda 2 to the power n minus 1. Likewise, you go on till you have 1 lambda n squared dot 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 till lambda n to the power n minus 1. And on the right hand side also you have known commodities, which are e to the lambda 1 t, e to the lambda 2 t dot 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 till e to the lambda n t. Now, I leave it to you again to check as an exercise that if the lambdas are distinct, then this is indeed a Vandermonde matrix, and you can check through mathematical induction or otherwise that this Vandermonde matrix is always going to be non-singular unless any two of the eigenvalues are equal. So, this is always invertible and you can always evaluate this. And now you might say, okay, fine. So, then you have only shown us that you can always evaluate these if the eigenvalues are non-repeated, which corresponds to the case of diagonalizable matrices, an easy case anyway. But what if there are repeated eigenvalues? Then it turns out that this is going to be singular, right? So, how do you go about that, or how do you bypass that? Well, it turns out in that case we do something very simple. So, suppose you come up with two equations that are identical. For example, you come up with a repetition 1 lambda. So, let me just write that down and we will end on this note. So, we have, for example, say e to the lambda 2 t is equal to phi naught t plus phi 1 t lambda 2 plus dot dot dot. This is without loss of generality. Let lambda 2 equal to lambda 3, yeah, plus phi n minus 1, sorry, have I, yeah, phi n minus 1, so I made a mistake there, phi n minus 1 t times lambda 2 to the power n minus 1. And then you get the same equation back again when you do e to the lambda 3 t. Remember, this is lambda 2 is equal to lambda 3 t. So, this does not generate any new equation. So, what do we do? What we do is quite simple, we take the derivative of this equation and generate another equation. Okay. So, we take the derivative of this equation, sorry, not this dd lambda. Okay. So, we take the derivative of this equation at lambda is equal to lambda 2, of course. So, that is tantamount to saying that you have this f and g and now they have some repeated roots, right, on either side. So, if they have repeated roots on either side, then of course they have repeated, then of course the function itself as well as its first derivative vanishes. If there are 3 repeated roots, then the function itself, its first derivative and its second derivative vanish. So, you can always keep taking as many derivatives as the number of repeated roots. So, if there are 2 repeated roots, you take the equation itself and its first derivative. If there are 3 repeated roots, you take the equation itself, its first derivative and its second derivative on both sides with respect to lambda. Yeah, so I shouldn't write, this is a little abuse of notation. So, I should probably say e to the lambda 2 t sorry, not lambda 2, lambda t at lambda is equal to lambda 2, and on the right hand side I do the same thing. So, when I do the same thing on the right hand side, what I will then end up with is, yeah, so what I will then end up with is, of course, this phi naught vanishes, but I will still have this phi 1 t plus phi 2 of t lambda 2, yeah, I think, yeah, if you take the derivative, plus phi 3 t lambda 2 squared upon 3. So, I think you will have a 2 here, right, yeah, that is simple. So, you will have phi 1 t, phi 2 t, yeah, so that is it. So, this is how we will go on till the last term you will have plus n minus 1 times phi n minus 1 t lambda 2 to the power n minus 2, yeah, and on the right hand side this of course devolves to just t e to the lambda 2 t. So, you generate another new equation like that. So, the moment you encounter repeated roots, this is how you go about by differentiating. So, in other words, we have shown you at least two distinct methods apart from the Laplace transform based method you might have been familiar with in order to evaluate the matrix exponential. Okay. In the next lecture, we shall take up this very important notion of controllability, which will relate to the zero state response part of the system that we have seen at the beginning of today's lecture. Thank you.